Welcome, my dear students. In the last class, I defined the how to represent matrix representation of a linear transformation, and in the end we show that the zero transformation is always we have a zero matrix. Whatever the basis is not depend on the basis. If we have a identity transformation, then we get a basis is according to the basis is the identity matrix, then the position of a this columns may be changed accordingly to the both basis of this. And also we say that this representation of matrix representation is mainly basic depend upon to the choice of the basis. If we have to change the basis, then the matrix representation is a change according to the basis. Okay, in this class we try to discuss some examples of related to matrix representation of a linear programming, a linear transformation. That means how we have to define such a linear transformation is defined according to the basis. We have to find the matrix representation. Okay, let's start with this problem. We take a linear transformation from R2 to R2, and we have a define is a linear transformation in the form of a t of x1, x2 is the form of a 8x1 minus 2x2 and x1 plus 3x2. Now we have to try to find the related to the ordered basis is this for R2 and the standard basis of R2. That means we have to calculate the first, we have to calculate the t of 1 1, and then t of 1 1 is equal to, according to this, is equal to 8 and 1. Then we calculate the t of 1 minus 1, then we have a t of 1 minus 1. Okay, sorry, this is not correct. Just a minute. We calculate the t of 1 1, that means is equal to 8. 8 minus 1 is equal to 6, and then is equal to 1 1 is equal to, we have a 4. 3 plus 1 is equal to 4, and then again we have to take t of minus 1, and then we have a 8 minus 1 minus 1 is 2, so this is equal to 10, and then we have a, this is equal to, you have a minus ka 2 is there. Now we have to write this 6 and 4 in the standard basis. Standard basis E, we have a this is our B and this is our C is equal to, we have a E1 and E2. So this 6 4 can be written in the form of a 6 times of a 1 comma 0 plus 4 times of a 0 comma 1. So we can say that t of 1 1 related to the basis of a C is equal to, we have a column vector 6 and 4, and accordingly this also we can say that we can write 10 and minus 2 can be written in the form of a 10 times of a 1 comma 0 plus minus 2 times of a 0 comma 1. Then we can say that t of this 10 comma minus 2 related to the basis C is a column vector is equal to 10, and we have a minus 2. Then we can say that t of related to the B and C can be written in the form of this is a column vector of this, then have 6 is equal to 4, and then we have a 10 is minus 2, and that means this can be we can say that this is the if we have a linear transformation defined by in this form, then we can say that this case is clearly is a basis of according to the basis of this is the we have a matrix representation of a this linear transformation corresponding to the basis B is this and the standard basis of a R. Okay, so now we have to, now this is what I just said that into this form. Now next we have to take this is a polynomials things, and we have is mapping defined from P2 P3 to P2, and map is defined into the this form, and basis is we have a B is the basis is this is a basis for this is the basis for you have a P3, and this is the basis for you have a P2. So that means we have to just calculate accordingly to the basis of a 1. basis of a 1 is equal to, you have a this is defined in the form of this form. This means we have a 1, this can be written in the form of t of 1 plus 0 into x plus 0 into x square plus 0 into x cube, and this is can be written as alpha 3 is equal to 0 plus you have a alpha 2 is equal to 0 plus alpha 3 is equal to, you have a 0, then you have a x is there, so this means you have a we have to write this form, and then similarly we just L is equal to, we have to write into this is 0, and then in this form. Okay, so this means we can just say that this is okay, I explain you 0 and x and plus you have alpha naught is equal to, you have a 1 plus alpha 1 is equal to, you have a 0 x square. This means we can say that this can be written as a x square. So t of 1 can be written in the form of a x square, and now we calculate this x square can be written in the linear combination of these two bases. So this can be written in the form of 0 into 1 plus 0 into x. So this is 0 into 1 plus 0 into x plus 0 into x square. So this means we can say that t of 1 corresponding to the basis C is a column vector 0 0, and this is equal to, you have a 1. So 0 0 1 is the corresponding to the this one. So this means we can say that, and okay, this is equal to this. First we just say that, so I just calculate t of, we have to write is equal to t of 1 of the corresponding the C is the form of the column vector of a 0 0 and 1. Now we have to calculate the t of x minus 1. This can be written in the form of a, you have a minus 1, we can write in the form of a this t of minus 1 plus x plus 0 x square plus 0 x cube, and this can be written as a alpha 3. Alpha 3 you have a 0, and plus alpha 2 is equal to, you have a 0, and just you have a 0 plus 0 into x plus you have a alpha naught. Alpha naught you have is equal to minus 1, and you have alpha 1 is equal to, you have a plus 1, and then you have a x square, and this is nothing but is equal to you getting a 0. So this means t of x minus 1 you have to getting the 0. This can be written as a 0 into 1, 0 into x plus 0 into x square. So we can say that, similarly we can say that t of, we have a x minus 1 over the C is the form of a, can write in the form of 0 0 0. This is the column. Now we try to the next one is we have a t of x minus 1 ka whole square. This can be written as a t of x square minus 2x plus 1, and this can be written in the form of a form of this. You have a alpha 3 is again you have a 0, and then you have a alpha 2 is equal to, you have a 1 plus 0 into x, and now you have plus alpha naught is equal to, you have a 1, and then you have a alpha 1. Alpha 1 is equal to, you have a minus ka 2, and then you have a x square. So this is nothing but is equal to, you have to get in the x minus ka x square, and now this x minus x square, this can be we can write as this in the form of a linear combination of this form. You have a 0 into 1 plus 1 into x plus you have to just say that minus 1 into x square, and this means we can say that corresponding to the this is, we have to say that t is equal to t of, we have a x minus 1 ka whole square is nothing but is equal to the column vector of a 0 1, and you have a minus 1. Now we have to calculate all these three. Now we have to take the last one. So this one I just said that into this form. So this means we can say that into this form. So I just stated this means we can say that we calculate the t of, you have a x minus 1 ka whole cube, x minus 1 ka whole cube, and then you can just calculate x cube plus 1, and then you have a 3 times of a x. So this means can be written as 3 times x cube is equal to alpha is equal to 1. Then you have a minus 2x minus 2x square, and in this form this can be if you want you can simplify this is equal to this. You have a x square, and then you have a minus ka 2x plus ka 1 is equal to you have a x cube minus ka 2x square, and then you have a this you have a plus ka this is minus ka 2x square, then you have a plus ka x, then you have a minus ka x square, you have a minus ka x square, and then this means you can just say that you can write in the form this is equal to minus ka 2x, or this is equal to minus ka 1. Okay, minus ka 1. Okay, so this means we can write in this form. So this is maybe some mistake here. I think so. We just said that this can be written in the form of a this form. Okay, just check. We have to check this. We have to x cube minus ka 2x square plus ka x minus ka x square minus ka plus ka 2 x minus plus ka 2x minus 1, and this can be written as you have x cube minus ka 3x square, and then you have a plus you have plus ka 3x, and you have a minus 2. So this is you have a 3 minus ka 3x square, and then you have a 3x. This is the correct. We have to calculate open this. This can be sorry, this is not correct. This is correct. So this means we can just operate the t. Now you have a alpha 3 is equal to you have a 1 plus alpha 2 is equal to you have a minus 3, alpha 3 is equal to plus 1, you have a x, and then you have a we check is alpha naught is equal to you have a minus 2, and then plus alpha 1 is equal to you have a plus 3, then you have x square. So this is can be written 1 minus 2x plus plus 2 this is minus 1 into 1 sorry, this is equal to 1, this is equal to 1, so this is means this can be written in the form of minus 1. So this is plus ka you have a 2x square. Oh, this is correct. So this means we can say that 1 minus 2x plus 2x square we can write in this form. Okay, so this is clearly we can say that. Okay, so we just write this is can be written in the form of 1 into 1 minus 2 into this. So this we can say t of, we can say that t of x minus 1 ka whole cube corresponding to the basis c is equal to nothing, column vector is equal to 1 minus 2 into 2. So complete matrix T with the we can write in the form of this. So this means we can say that complete matrix T with the corresponding the basis B and C is nothing but is equal to you have a 0 0 1, this is you have a 0 0 0, then you have a 0 1 minus 1, now you have a 1 minus 2 and 2. So this is the correct value of this we have to calculating it. So this way we just say that is equal to into this form is this form. This is nothing but is equal to we have a t of b of c is equal to this form. Okay, so now I think you have a clear about this. Now we have a one more example. We try. I take a this we have to take a basis is equal to e1, e2, e3, and we take a c is a different types of a basis. So I just take a we calculate the first is equal to t of e1, and t of e1 is nothing but is equal to from this you can just say that here 1, here 2, and there is equal to 1. So you can say that 1 and 2 and 1, and this means we can say that this 1 to 1 we have a 1 to 1 can be written as a finite linear combination of this. So we have to write alpha 1 0 plus beta times 1 2 3 plus gamma times minus 1 0 1, and this giving you a alpha plus beta minus gamma, and then you have a alpha plus 2 beta, and then you have a 3 beta plus gamma, and if you simplify it, alpha plus beta minus gamma is equal to 1, and then you have a alpha plus twice beta is equal to, you have a 2, and then you have a 3 beta plus gamma is equal to, you have a 1. Now if you have to subtracting these two, what we getting, this alpha is cancel out, so we getting is equal to minus beta, and then you have a minus ka gamma is equal to, you have a, we have to subtracting this, so you have to we have to just subtracting this is equal to, you have uh, uh, this this is minus, so this is minus minus ka 1, and then we can say that this is can be written as a beta plus gamma is equal to 1, and also we have a 3 beta plus gamma is equal to, I just check is this 1 2 is correct or not. 1 2 and we have a 1. Okay, so this is the, I just check 1 2 1, and then we have to just take, you have a clearly you have a from here just if you subtracting this, so you have a beta is equal to 0. Okay, the beta is equal to 0, then beta is equal to 0 means you have a gamma is equal to 1, and you have a alpha is equal to 2, so we can write as the form of a 2 0 and 1. Now we calculate what is our t of e2. Now t of e2, just check his here, we have a minus 1 3 and 1, so you have a minus 1 minus 1 3 and 1, so this is minus 1 3 and 1. Again we try to check from here, we have alpha plus beta minus gamma, so we have alpha plus beta minus gamma is equal to minus 1. See my alpha plus 2 beta, alpha plus 2 beta, this can be written in the form of a alpha times of a 1 1 0 plus beta times of a 1 2 3 plus gamma times of a minus 1 0 1. So this means we can say that this is nothing but is equal to alpha plus beta minus gamma, and then you have a alpha plus 2 beta, and then you have a 3 beta plus gamma, so this is equal to minus 1, and then you have alpha plus 2 beta is equal to 3, and you have a this is, sorry, this is not a minus, you have a 3 beta plus gamma is equal to, you have a is equal to 1, and now again from these two, subtraction of these two, we can just take is equal to minus ka beta minus ka gamma is equal to minus ka 4, so this means is we can say that we have a beta plus gamma is equal to 4, and now you have minus minus minus, then you have a this is equal to twice beta is equal to, you have a minus ka 3, so beta is equal to, you have a minus ka 3 by 2, and beta is equal to minus ka 3 by 2. You calculate all others values simply because you have a beta plus gamma, so gamma is equal to 4 minus yani plus 3 by 2, so you have a 11 by 2, so gamma is equal to 11 by 2, beta is equal to this, and then you have a twice beta is equal to, you have a sorry gamma alpha we have to, from the second equation, alpha can be written as a 3 minus 3 beta, and then can be written in the form of a, you have a again alpha in this form, so we just take a in the form of a 9 3 by 2 and 11 by 2 is this clearly, and now we have to similar fashion we calculate the E3 is equal to, this is the form of a like this. Again if you want to just say that alpha plus beta minus gamma is equal to 1. Now you have a, I think so, alpha plus 2 beta, we have a alpha plus twice beta is equal to, you have a minus ka half, and then you have a 3 beta plus gamma, so you have a plus gamma is equal to minus 2. Again by just first 2 we just take it in the form of this subtracting this, so you have a minus ka beta minus ka gamma is equal to this is plus, so 2 plus 1 is equal to 3 by 2, and then you have a 3 beta plus ka gamma is equal to minus ka 2, so this is we can say that this is equal to 4 of beta is equal to, you have a 3 by 2 is minus ka 1 by 3, and this we simplify this, you can getting beta is equal to minus ka 1 by 4, and if beta is equal to minus 1 by 4, we can rest of them also calculating. So E3 is equal to this one. So we just say that T of E1 with the C is equal to, you have a column vector 2 0 1, and now T of E2 we have a corresponding to the C is a column vector 9 minus 3 by 2 and 11 by 2, and now we have a T of E3 with the C we can say that is equal to column vector 0 minus ka 1 by 4 minus ka 5 by 4, and now by this we can say that clearly T of this B corresponding to the C is a matrix of the form of equal to 2 0 1 9 minus 3 by 2 11 by 2, and then you have a 0 minus ka 1 by 4 minus ka 5 by 4. So this is the answer we have to getting into this form. So this means clearly T of C is equal to is this form. This completes the solution of this problem. Okay, now I just take some different types of a matrix. This linear transformation, where linear transformation we define from P2 to 2 by 2 matrices, where this is defined in the form of a map, a linear map. It is defined from polynomials to P2. This means the basis of this is equal to, you have a 1x and x square, and this is the standard basis for m by 2 by 2 matrix. These are the two are the clearly these two are the standard basis for this thing. So we just take one by one. I just take a, for example, we calculate T of 1. T of 1 is nothing but is equal to, we have to take a matrix, and the matrix of the form we have to calculate the derivative, because whatever polynomials we have is the polynomials Px is equal to, we have a 1, so this means we have to take a fx Px derivative is equal to 0. So this means this corresponding to the T of we have a 1 is nothing but is equal to a matrix of the form this derivative is equal to 0. 1 is 0. There are 2 of P of 1, T of 2 times of a P of 1. We just take a P1, Px is equal to 1. So you have a P1 is also you have a 1. So this is equal to 2, and the second derivative is 0. So this is equal to 0 into 0. And also we can calculate the x. Then we have a P of x is equal to, you have a x, then P of derivative of x is equal to, you have a 1, and then you have a P of double derivative of x is equal to 0. So T of x can be written in the form of a matrix P of P prime 0 is equal to 1, and now twice times of a P1 is equal to 2, and then P1 is equal to 2. Then we have a 0 and 0. Then we have to calculate the P of T of x square. You know that this P of x is equal to, you have a Tx square, means you have a P of x is equal to x square, then you have a P of derivative is equal to 2x, double derivative of this is equal to 2. So this can be written in the form of a P of P prime 0 is equal to 0, 2 times of a P of 1 is equal to, you have again 2, and then you have a 0, 2 times of a P double derivative is equal to, you have a 4. So this is a matrix into this form. Okay, so we calculate all this matrices into this form. That means we have is this form. Now next is we have to write this matrix as a linear combination of a this basis, this matrix as a linear combination of this matrix, and this is also into this form. So the first one we getting is equal to 0 to 2. So this can be clearly, you have a, I just explained you 0 to 0 0. Then we can write in the form of a 0 of, you have a 1 0 0 plus 2 times of a, you have a 0 1 0 plus you have a 0 times of a, you have a 0 0 1 0 plus 0 times you have a 0 0 0 1. Then we can say that this is equal to T of 1 corresponding to the basis C is a column vector, you have a 0 2 0 0. Similar fashion we can calculate the next one. So this is equal to next one. Now next one is you have a T of x 1 to 0 0. So this means T of x is equal to, you have a 1 2 0 0. Then you have to write the 1 2 0 0, this can be written as a 1 into you have a 1 0 0 0 plus 2 times you can write 0 1 0 0, and we can say that this is again you have to plus times 0 times of you have a 0 1 0 and plus 0 times of a 0 0 0 1. So this means we can say that T of corresponding to X, this is C is a column vector is equal to 1 2 0 0. So this means we have a like this, and now next is we have a T of X square. So T of X square, you have a matrix in the form of a this is 2 0 0 2 4. So we can say that this is nothing but is equal to you have a 0 0 2 4. This can be written as 0 times of a 1 0 0 0 plus 2 times of a you have a 0 1 0 plus 0 times you have a 0 0 1 0 plus 4 times you have a 0 0 0 1. That means we can say that T of X square corresponding to the basis of C is a column vector. You have a 0 2 0 4, and then we can say that finally we have a T of this linear transformation T corresponding to the basis B and C can be written in the form of a, we have a first is corresponding to 1, we have a 0 2 0 0, and this is equal to 1 2 0 0, and then we have a 0 2 0 4, and this is the matrix we have to getting for this. Clearly we have this, so hence we have a like this, you have a clearly we just say that we have all these things equal to 0 0 0 2, and then we have a 1 2 0 0 2 0 2 0 4. So this is the our matrix representation of a linear transformation map from T from P2 to M 2 by 2 matrices. Okay, so now I just try to one more example. I take a linear transformation into this form, and I take a basis are two different type of a basis. First I take a standard basis, then it's very trivial for a standard basis. I just take if you take a T of 1 0 0, this is nothing but is equal to you have a 3 and you have a 3 1. So this is going to R2, so 3 comma 1, and 3 comma 1 can be written as a 3 1 comma 0 plus 1 comma 0 comma 1, and then we have a T of 0 1 0. This can be written in the form of a, you have a minus 2 and then you have a minus 3. This can be written as a minus 2 1 comma 0 and plus minus 3 0 comma 1, and now we have a finally we have a 0 0 1. This is nothing but is equal to you have a 1 comma minus 2, and this can be written as 1 times 1 comma 0, and then we have a plus minus 2 times of a you have a 0 comma 1, and then by this we can say that this is matrix can be written in the form of a clearly we can write the matrix of a this. So this is nothing but is equal to matrix in the form of a, you have a 3 comma 3 comma 1, then we have a minus 2 comma minus 3, then you have a 1 comma minus 2, and this is you have a T corresponding to the B and C for a standard basis. Okay, so now I just say that whatever this. Now I want to change the basis of this. The same question I just say that whatever map is defined is this way. 3 this is 3 1 minus 2, and then V1 minus 3 V2. I just take a this map same, and then I just change the basis into this form. So I just take first is defined is equal to V1 V2 V3 in the form of I define the form of a 3 V1 minus 2 V2. So we have a 3 V1 twice V2 plus V3, and then next is we have a V1 minus 3 V2. We have a V1 minus 3 V2 plus twice V3, and this map is defined into a okay, this is okay, this is okay minus 2 V3. This is we have a minus 2 V3. Okay, so now this is the basis B, this is the basis C, this is the standard basis, and this is the basis. I change the order of this standard basis. I just change the better basis of order of this basis. So I have a 0 1 0, then 0 1 0 can be written as a you have a -2 and -3, and then can be written in the form of a -2 times 1 0 comma 1, and then you have a we can write this is equal to, you have a -3 times you have a 0 comma 1 plus 2 times of a -2 times of a you have a 1 comma 0, then you have clearly written the form. Then this is the t of 0 1 0, which is corresponding to the basis C, is equal to column vector -3 -2, and the similar fashion other we have to calculate the t of, we have a 0 0 1 is nothing but is equal to, we have a 3, you have a 1 and -2, and this can be written in the form of a -2 times you have a 0 comma 1 plus 1 times of a you have a 1 comma 0. So in this case we have a t of 0 0 1. This matrix column vector is nothing but is equal to -2 and 1, and the similar fashion we have a v3. So v3 is nothing but is equal to v1. So this is equal to, we have to, I just directly write, is equal to, you have a 1 0 0. This is a C. Is the form of this, you have a 1 and you have a 3. So this is a matrix of this T corresponding to the basis B, and C is the form of a, we have a this is equal to, you have a -3 2, and then you have a -2 1, and then you have 1 and 3. So I just change the position of a matrices, then clearly just say that this matrix is new into a this matrix we have to get into this. So now I just say that I have to discuss various examples and also this various types of problems. We have to different types of basis we have to choosing some, and we getting the various type problem. We have to finally getting the some transformations matrix corresponding this transformation from B to C. So I think you have a very clear about how to calculate a matrix transformation by using the standard basis of this thing. Okay, some basis, if we have to change the basis, now clearly I change the same basis, but I change the, in this case is a, I change the orders of a basis. Then after change the order of a basis, my matrix, new matrix is look like is this form, which is not the similar for the previous one. You can see this is clearly present the same matrix, but we have to this is first this, and the columns is also shifting is accordingly. So this means we can say that this representation of a linear transformation in the matrix form is very important. What is the order of a basis we have to, if we have to change the order, then accordingly the transformation of a basis is also changed accordingly. So I have to stop today's class here, and in the next class I try to discuss some property of this matrix transformation. That means we take a already studied that the sum of a two linear transformation is a linear, and also we know that the composition of a two linear transformation is also a linear. Then now see that what about the, if we take a sum of a two linear transformation, what is the matrix transformation of a sum of a two linear transformation, and what is the matrix transform representation of a composition of a two transformations. So this we discuss into the next class. I have stopped today class here, and thank you very much for this.